Charlene Balaod.
I am Krysha Tero.
I am Perales.
And we are the reporters of the fundamental theorem of arithmetics.
Hi, good day everyone. I am Charlene Balaod, and today we will be talking about fundamental theorem of arithmetic. Fundamental theorem of arithmetic is also called as unique factorization theorem. So fundamental theorem is basically a factorization of a number by using prime number. So it is to broken down number using prime numbers. So first, we have to determine the numbers that are composite or prime. So what do we mean by prime?
Prime numbers are numbers that have only two factors, one and themselves.
On the other hand,
A composite number is a positive integer that can be formed by multiplying to smaller positive integers.
so below are the examples. So basically, it's the factors of 36, which is 6 times 6, 9 times 4, 12 times 2, and 18 times 2. Now let's proceed to Theorem 3.1. The Theorem 3.1 states that if P is prime and P divides AB, then P divides A or P divides B. So basically, theorem number 1 has this equation, which is P divides AB would also be P divides A or P divides B. As we said, P is prime, so therefore let's assume that our P is 7 and our AB is let's just say 56. Okay, so we should take note that the 56 should be a product of two numbers. And now we have to go back to the 56 and then find its factor. So we have to choose a factor that has at least one number that is divisible by 7. So let's choose 28 and 2. So our A would be 28 and our 2 would be the B. And now we have to prove either P divides A or P divides B. We can use the formula P times the constant equals A. So we have to get the constant. We should also remember that that constant should be a positive integers. We can either use that formula or just simply dividing the P and A to get the quotient, which is a positive integer. So basically, the answer for 28 divided by 7 is 4, right? And it is a positive integer. Therefore, we have already proven that P divides A. And by that case, we no longer have to proceed because we have to put emphasis on the statement that is or. If we have proven P divides A, then we no longer have to prove P divides B. Now let's proceed to the corollary 1. By the way, what is corollary?
In mathematics, a corollary is a theorem connected by a short proof to an existing theorem.
The first corollary states that if P is a prime and P divides A sub 1, A sub 2 up until A sub n, then P divides A sub k. By using the equation, which is P divides A sub 1, A sub 2, A sub 3, so on, up to A sub n. Now let's assume that our P, which is the prime, is 3. And we have the number of 2016. Okay? So now, all we have to do is we're going to have the factors of 2016 that is same as A sub 1, A sub 2, and so on. So we'll have 4 times 7 times 9 and times 8. So if we if we multiply all those together, we'll get 2016. Okay. So in order for us to prove the theorem, we have to distribute the prime, which is 3, and multiply to all the factors. And we're going to identify which of those have a constant, or let's just say a quotient, that is a positive integers. At least one of it. By just looking at it, we can conclude that it is 3 divides 9, right? So that gives us the answer that is a positive integers. So going back to the theorem, which is then P divides A sub K. Actually, that K could either be A sub 1, A sub 2, and so on. So in this case, our 3 is say A sub 3. Therefore, our P times A sub K is P times A sub 3. I hope I am understood. Going on to the corollary 2, which is basically somehow the same as the corollary 1, only that all the factors of the assumed numbers are all prime numbers. So if we have the equation, which is P divides Q sub 1, Q sub 2, and so on up to Q sub n. Now let's have an example as 7 as our prime number, and let's just assume that we have let's just say 4,641 as our number, and we're going to get its factors that should be prime, that all of it should be prime numbers. So the factors would be 13 times 3 times 7 times 17. So everything is prime. So if we multiply that all together, we'll get 4,641. So the same process, we have to distribute and multiply the 7 to all the factors. Then we have to identify which among those can give us a positive integer as a quotient. So as we can see, it's the 7 times 7 that would give us a positive integer, which is 1. And same goes to the corollary 1. We have to find the k of P divides Q sub k. So basically it is 1, 2, 3. It's the A sub 3, right? So therefore it's PQ sub 3. I mean Q sub 3. Because the position of 7 times 7 is Q sub 3. In that specific Q sub 3, or the 7 times 7, is what makes the theorem right. Thank you, and I hope you have learned something. So thank you so much for listening. Now I will give you the floor to Miss Krysha Tero for the Theorem 3.2.
Hello, again, I am Krysha Tero, and today I will tackle about Theorem 3.2, which is the fundamental theorem of arithmetic. So this theorem states that every positive integer n is greater than 1 is either prime or product of primes. This representation is unique, apart from the order in which the factors occur. So let's talk about prime. So prime number is a number greater than 1 with only 2 factors themselves and 1. So example of prime numbers are 2, 3, 5, 7, 11, 13, 17, 19, 21, 31, and so on. So in this theorem, we will use the prime factorization. Prime factorization is to write a number as a product of its prime factors. So there are 2 ways in writing a prime factorization: the repeated division method and a factor tree method. So prime factorization is similar to factoring a number and considering only the prime numbers like 2, 3, 7, 11, 17, and so on among all the factors. So to further understand this theorem, let's have an example. So to prove the Theorem 3.2, which is the fundamental theorem of arithmetic, so either n is a prime number or it is a composite. In the former case, there is nothing more to prove. So if n, or the positive integer, is already a prime number, so there is nothing to prove. But if n is a composite number, then there exists an integer d satisfying d divides n, and d is less than n but greater than 1. For example, is 360. So 360 is a composite number. So we'll use the prime factorization to find the prime factors. So in finding the prime factorization, either we'll use the repeated division method or the factor tree method. So it doesn't matter how you split your composite numbers, you always get the same prime factor. So 360 is a composite numbers. If we will split 360, we'll get 2 and 180. And 2 is already a prime number, so we will split 180. 180 is a prime. 180 it can be split into 2 and 90. And 90 can be split into 3 and 30. 30 can be split into 5 and 6. And 6 can be split into 2 and 3. So we collect a prime factors like 2, 2, 3, 5, 2, and 3. So in writing a prime factors, we will write into ascending order from smallest to greatest. So 2 and 2 and 2 and 3 and 3 and 5. So if we will multiply all of these prime factors, 2 times 2 times 2 times 3 times 5 times 5, we will get 360. Next example is 180. 180 is again a composite number. We'll use a prime factorization here. So 180 can be split into 2 and 90. 90 can be split into 2 and 45. And 45 can be split into 3 and 15. 15 can be split into 3 and 5. So final 3 and 5 are already a prime number. So we will have a 2, 2, 3, 3, and 5. These are all prime numbers. So if we will multiply 2 times 2 times 3 times 3 times 5, we will get 180. So the prime factors of 180 are 2, 2, 3, 3, and 5. So the third example is 97. I have a question. Is 97 a prime or a composite number? Yes, you get it right. 97 is already a prime number. So Theorem 3.2 states that if fn or if a positive integer is already a prime number, so there is nothing to prove. So 97 is already a prime number. Another example is a higher positive integer, which is 1000. 1000 is a composite number. So we will split 1000 and find the prime factor. So we'll use the 3 method prime factorization. So 1000 can be split into 2 and 500. And 500 can be split to 10 and 50, right? Since 10 is a composite number, we will split 10. We will get 2 and 5. So 2 and 5 are prime numbers. So we will stop there. 50 can be split to 5 and 10. So since 5 is already a prime number, so we will not find another factors of 5. So 10 can be split to 2 and 5. So 2 and 5 are already a prime number, so we will stop here. So 1000 have a prime factors of 2 and 2 and 2 and 5 and 5 and 5. So if we will multiply 2 times 2, 4 times 2, 8 times 2 times 5 rather is 40 times 5 is 200 and times 5 is 1000. So we will have 1000 here. So the prime factors of 1000 is 2, 2, 2, 5, and 5.
So by collecting like primes and replacing them by a single factor, we can rephrase Theorem 3.2 as a corollary. So corollary is any positive integer n greater than 1 can be written uniquely in a canonical form.
So to illustrate the canonical form of the integers, the sample integers in the earlier, like 360, 360 has a prime factors of 2 into 2 into 2 into 3 into 3 into 5. So the corollary states that in a canonical form, written uniquely in a canonical form. So 360 has 2 into 2 into 3 into 3 into 5. So we will only count the number of 2. So since we have total number of 2 is 3, so 2 is 2 cube times 3, we have 2 3's, so 3 squared times 5. So if we will multiply this 2 cubed times 3 squared times 5, we will get the same answer, which is 360. So another example is the 180. So 180 has a prime factors of 2 is to 2 is to 3 is to 3 is to 5. So the same process, 2 squared times 3 squared times 5. So we will get 180. And another example is 1000. 1000 has a prime factors of 2 into 2 into 2 into 5 into 5 and into 5. So 2, there are 3 number 2 here, so 3 cubed times 5 cubed. So we will get again 1000. So that is the process in writing a canonical form. Thank you.
Hello everyone, this is Perales, and let's proceed to the last theorem, which is the Theorem 3.3, or the Pythagoras. The number square root of 2 is irrational. Supposed to be the square root of 2 is rational. That means it can be written as the ratio of two integers p and q. So, square root of 2 is equals to p over q. We may assume that p and q have no common factors. So let's square both sides. So squaring both sides in the first equation gives 2 is equal to p to the power of 2 over q to the power of 2, which implies p to the power of 2 is equals to 2q to the power of 2. Thus, p to the power of 2 is even. The only way this can be true is that p itself is even. But p to the power of 2 is actually divisible by 4. Hence, q to the power of 2 and therefore q must be even. So p and q are both even, which is a contradiction to our assumption that they have no common factors. So, the square root of 2 cannot be rational. And that would be all. I hope you learned something from our report. Thank you and God bless us all.